Hello everyone, today we'll talk about the solution to the problem design a stack with increment operation. We want to start with a normal stack and add a single operation to it. That increment operation wants us to increment the k bottom elements of the stack by some given value. So we all know what a stack is. Let's say, imagine it horizontally. We can add elements to the end, and that's the only way of adding elements. And we can remove elements from the end, and that's the only way of removing elements. And elements stay in line for the whole duration. So, in terms of last in, first out, or first in, first out, this is a last in, first out data structure. And we want to add this increment operation, so one thing that we can do, of course, let's try to think about how to implement a normal stack first. You don't have to reach for any specialty libraries. That's because a stack wants to be able to add elements to some end and remove elements from that same end, and that's it. So a normal list, the Python list, is very well suited to this task. Because it will grow as necessary, we can add elements to the end and remove elements from the end in constant time. Right. By using a list under the hood, we can implement this increment operation very easily. We can just iterate through the bottom k elements and increase them by the value. So that's easy, but that of course is slow. That means that the increment operation will behave in time proportional to the size of our stack. So we want to find something better. And to solve it in a better way, we can use the same trick that might be used to solve a problem of having some number of range additions. So you have an array that starts with some values, and then you have some number of range additions. So for instance, +4 on this range, then you have +1 on this range, then you have -2 on this range, and at the end you're being asked to return the values of all the elements. So the total number of elements touched and the number of times each element is touched by a range update may be very big, maybe quadratic, but since we only want to give the final value, instead of adding the values to every element in our array, we can just maintain in a separate array, which starts with all zeros. We can mark a 4 when this interval of +4 starts, and -4 after it ends. And 1 where this thing begins, -1 when it ends. And of course, when two intervals are touching, then they will modify the same value. And after we have all those operations, because now every interval takes constant time, and after that we can calculate the final values of all the elements by just calculating the prefix sum of this second array. So for instance, we see that elements here will be changed by 0, elements here will be changed by 4. This element will be changed by 4 plus 1 equals 5. Now those elements only by 1, this element by 0, this element by -2, and those elements by 0. So by calculating this prefix sum in normal linear time fashion by just going from the left and accumulating the sum, we can calculate the final differences and so the final values. And we can do a similar thing here, and that's because of this bottom k elements clause, which is not, for instance, a top k elements clause or any element. That's because, since we have this stack property, this last in first out property, when we look at the k bottom elements of the stack, then how can they change? Well, as long as there is something to the right of this block, then nothing can happen to this block. As we mentioned, the only way of adding or removing elements is adding or removing elements from the right. Of course, there may be some other increments, but let's focus on a single increment for now. And how can it change later? Well, we can also now start removing elements from the top, and then maybe adding some more elements on top of that. So, what do we know? We know that we increment the last k elements, and we can just remember the fact that we incremented them. And whenever we remove an element, assuming that we know its proper value, which of course we'll show how to do in a second, we now remember that k-1 elements are incremented. And of course, if there are many increments, then we remember all of them. And the easiest way of remembering them is just to mark the topmost element that's incremented with the value of an increment. And this is where this solution, this idea from this different problem, comes in. So for instance, we can have our stack with some values, and maybe we have here a 1, and here a 3, and here we have zeros. So this represents a situation where we incremented the bottom 6 elements by 3, or maybe more. Let's say we incremented bottom 8 elements, but then we removed all the elements until 6 remained. Anyway, we have the bottom 6 elements incremented by 3, and then also 4 bottom elements incremented by 1. And that means that whenever, and of course, the thing to remember here is that when we pop this element at some point, we give its value plus 3, and you have to remember that now only 5 elements are incremented, so we move that 3 here, and this becomes a 3. And again, if we pop this element now, then this becomes 3 plus 1, so this becomes 4. So we can propagate those updates to the left, and this is very intuitive in that it's as if we have incremented one fewer element. And that gives us the increment operator in constant time, because again, we only have to access not the bottom k elements, but the kth element from the bottom, which we can do in constant time because of how the list works. And now all the operations are in constant time. So, and of course, for this max size, we just remember that max size and keep in mind not to exceed it. So when we want to add an element, we check if the size is equal to max size. In that case, we don't do anything. Otherwise, we append a new value. We'll be maintaining pairs of values. So the real value and the modification, which starts at 0. When we pop an element, if there is nothing to pop, we return -1, as we're being asked to do. Otherwise, we get from the top of the stack by popping the value and the current difference. We have to propagate the difference if there is anything remaining on the stack. So if the stack is non-empty, we just take the last element of the stack and we increment its difference by our difference, and of course at the end we return the value plus its current difference. And for incrementation, again, on an empty array we don't do anything. We are being asked that if there are less than k elements, we increment all of them, so we modify k to be the minimum of the length of our data and k, and we increment the kth element from the bottom, which might be just the top element, by adding value to its difference. So a very clean solution using a very useful, well, not maybe that useful, but a common and easy to implement trick in a novel context.